Hi, Mr. Sapone here, and today we're going to solve a mole problem. It's a little complicated, there's a lot of steps involved, but I think we can do it. I think you can do it. If I were to give you one atom of gold for every second that has elapsed since the dinosaurs went extinct 65 million years ago, how much gold would you have? And I'm asking for what volume of gold, like what physical size of gold. A nugget, a rock, a building, a truck, a microscopic piece you could not see. Assume the density of gold is 19.3 grams per centimeters cubed. That's the density of gold. I'm asking you for a volume. Hopefully this is kind of evoking a formula you might want to use. Um, so we have the periodic table box for gold, and we rounded this to 197. So 79 protons, 197 grams per mole. Hopefully we're seeing that we should be using a density formula. Density equals mass divided by volume. And if you rearrange this, you bring the V up, bring the rho down, volume equals mass divided by density. And we know the density of gold. It's given to us in the problem, 19.3. And I ask you for a volume. So really, if you can figure out the mass of gold that you'd have, you can plug it in and solve for the volume. And it's going to take a few steps to do that, though. What do I tell you? I tell you that I give you one atom of gold for every second that went by in the last 65 million years. So for every second that went by, you got an atom of gold. So how many atoms of gold did you get? Well, you got to figure out how many seconds there are in 65 million years. So this becomes a conversion problem factor. We have to convert 65 million years into seconds. So we're going to start with 65 million, 4, 5, 6 years times, the first thing I want to do, I have years up here, I want to put years down here. 1 year is 365 days. So if we multiply it across, that would tell us how many days there were. But we don't want days. And of course, we're ignoring leap years and crazy astronomical events and other things like that. So these years do cancel, and I'm left with days, but I want to get rid of days. 1 day is 24 hours. And again, these days are going to cancel. We're doing a simple unit conversion. We're converting 65 million years into seconds. How many seconds are in 65 million years? Times. We have an hour up here, so I want hour down here. 1 hour is 60 minutes. And hours cancel, so I've got my unit from 65 million years to minutes, but I have to go one step further. I know 1 minute is 60 seconds. So now you just multiply across. The bottom we have a whole bunch of ones, so we can just get rid of all these. We don't need them. So just multiply all these numbers across, and that tells you how many seconds went by in the last 65 million years. And that number is exactly how many atoms of gold I have given you. And when you do that math out, you end up with 2 times 10 to the 15th atoms of gold. So you're given 2 times 10 to the 15th atoms. And now we got to figure out what to do from the number of atoms to figure out the mass. How do I know how much that many atoms of gold will weigh? What is the mass of that many atoms? Well, hopefully you realize you need to use Avogadro's number. First, we're going to convert atoms into moles. Atoms into moles, and then moles into grams using the molar mass of gold. So the first thing we're going to do is ask how many moles is 2 times 10 to the 15th atoms. And we use Avogadro's number, 6.022 times 10 to the 23rd. A mole of anything is 6.022 times 10 to the 23rd of that thing. If you had a mole of eggs, you'd have 6.022 times 10 to the 23rd eggs. If you had a mole of Legos, you'd have 6.022 times 10 to the 23rd Legos. The word mole simply means this number, just as the word dozen means 12. So it's always that same. So we're going to use Avogadro's number. So we're starting with the number of atoms we have. We have 2 times 10 to the 15 atoms of gold, AU, gold, and I'm multiplying it by a conversion factor. I know that 1 mole of gold is equal to 6.022 times 10 to the 23rd atoms of gold. 1 mole of anything equals this quantity of it. So the cool thing here is I get atoms to cancel. So now you multiply 2 times 10 to the 15th times 1, divided by 6.022 times 10 to the 23rd, and we end up with 3.3 times 10 to the negative ninth moles of gold. So we converted this many atoms into moles using Avogadro's number. So I know I have not even close to a mole. I have 10 to the negative ninth of a mole, 0.0000. With a decimal point, I don't have even close to 1 mole of gold. And hopefully, if you had 1 mole of gold, you'd have 197 grams of gold, because gold is 197 grams per 1 mole. And you have a very small fraction of a mole, which means you have a very small fraction of 197 grams. So we have that many atoms of gold, 2 times 10 to the 15th, which is 3.3 times 10 to the negative ninth moles of gold. So now we're going to convert moles of gold into grams of gold using the molar mass, using another conversion factor. And all you got to do is take the quantity we have, moles of gold, and we have 3.3 times 10 to the negative ninth moles of gold, and we got to set up another conversion factor. I have mole of AU here, I want mole of AU down here. 1 mole of gold is 197 grams. So all you have to really do, and this cancels, is multiply 3.3 times 10 to the negative ninth times 197 grams, and you end up with 6.5 times 10 to the negative 7th grams. So if I gave you 1 atom of gold for every second that went by in the last 65 million years, you'd have 0.123456 grams of gold. A very, 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 very small amount. Not a tenth, not a thousandth. We're talking almost a billionth, maybe a millionth to 10 millionth of a gram of gold. A very, very, very small amount, not even measurable. So, and now that you know that mass, we solve for the mass of gold I'm giving you. Just plug that back into the density formula, and that'll allow you to solve for the volume. And when you take your density formula, which is mass divided by, or volume equals mass over density, put in the mass we solve for and divide by the density of gold, it gives us the volume of gold that I've given you, which is 3.4 times 10 to the negative 8th centimeters cubed. Again, an extremely small amount. Definitely not visible. The smallest we can see is a little dot like 0.01 centimeters. You can't even see that with your naked eye. It's such a small, 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 small amount. Times 10 to the negative 8th centimeter. Centimeters are already small, and you have a very small fraction of a centimeter. So essentially, if I gave you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. If I gave you this many atoms of gold, it would amount to absolutely nothing. And that just shows you how small the atom is, how many atoms there actually are in things. Thousands, it's a million, billion, trillion. So I give you 2 quadrillion atoms of gold. You don't even have anything you can see or measure. In fact, it's so small you could never say I didn't give it to you. I said, well, I gave it to you. You must have lost it. I put it in your hand. But you can't actually see it or feel it. It's immeasurable. I wouldn't even be able to count that out and give it to you. But so the idea is just that atoms are really, really, really small, and we got a little practice converting between moles and grams and doing a complicated multiple part problem. So when you're given one of these on a test, and I will undoubtedly switch this up, the steps will be the same, but I'll change the years. I'll change it to something else. I'll use the formula volume equals mass over density to solve, but you got to figure out what m is. So convert the time into seconds, figure out the number of atoms you have. Once you have atoms, we go atoms to moles using Avogadro. Then we go moles to grams. Plug that back in and solve. Yes, a very dense problem, but you are capable of doing it if you take your time and sit through it and work it out. This is Mr. Sapone.